All right, so today we're going to talk about tooling. You've been exposed to many tools so far over the last 8 weeks, and some of them have just been exposure level. Others you've really gotten your hands dirty with and started working with. And these are all important tools that you'll be using throughout your careers. The first one that we introduced you to was version control, right? The software versioning control systems. And in particular, the one that we use is Git, right? But remember that that's not the same thing as GitHub. GitHub is just a website that allows you to store your repos in the cloud, usually for free. GitHub was started, I think, 15, 20 years ago. I forget what it was. It was eventually bought out by Microsoft, which at the time everybody thought, including myself, thought, oh no, this is going to destroy GitHub. They've surprised us all, and they actually freed things up and made unlimited repos for free and stuff like that. But what is Git itself? Well, it was created by Linus Torvalds. Does anybody know who that is? The Linux, right? That is named for Linux, right? So he was really unsatisfied with the version control systems that existed out there, and so he said, "Screw this! We're just going to make a new one here." It was not the first distributed version control system. They're old. In fact, there's older version control systems. There's CVS, which is control version system. Then that was taken over by Subversion or SVN, and then we had truly distributed version control systems. And what we mean by that is that a complete copy of the entire repo's history is available on every single copy. So if you clone something, you're not just cloning the code in that repository, you're cloning the entire history. You can go back in time to 5 months ago and see what the project looked like. Basically, the distributed version control systems keep track of differences. So if you change code like on 5 lines, it doesn't store the entire thing. It only stores those changes in its history. It's not the first one, of course. There was another one called Mercurial, if you've ever heard of that. But at the end of the day, Git won out, all right? And now Git is king, and you've been using it to clone stuff. Hopefully you've been using it to actually store stuff, right? You have been without knowing it. Anytime that you go into code spaces, where does it save that code? It saves it to a repository somewhere. But hopefully you've actively been using it with your actual code just to keep track of stuff. Or if you've teamed up in a pair, hopefully you've been using Git the entire time to share code, right? It allows you to store multiple copies of those on each of your computers, and then also push it to the cloud on GitHub if you've been using GitHub. By the way, GitHub is not your only option. If you want to, you can go ahead and use GitLab, git.unl.edu. It's an alternative to GitHub. It's GitLab, which is an open source software. And we have one hosted here at UNL. If you want to go to git.unl.edu and use your UNL credentials there. It's a little bit more open. I don't think that there's any repository size limits, nor there might be, I don't know. But you can always ask them, hey, can you increase the size for my quota or whatever. And it will be active as long as you are a student. So make sure that when you graduate, you grab whatever you need off of there, because they might shut it down after you've graduated. But yeah, that's a GitLab instance that's hosted by UNL. It's great. It's convenient, right? If you're working with a partner, you always have a backup. I always tell this story. Several years ago, a software engineer came to me and said, this is for like discrete math homework, which they do have to program in my discrete math courses. But he came up to me and said, everything was wiped out last night. What do I do? And I go, weren't you using Git, right? And no, I was not. Well, don't you use it in all of your classes? Yes, but not in your personal life? No. You see why now, right? You at least have a backup that you can go to that's sitting up on GitHub or something like that. And like I said, it's perfect for team development, right? Don't go. It's not 1999 anymore. Even in fact, 1999 wasn't even 1999. You don't transfer via a Dropbox or a Google Drive or a OneDrive. You don't pull out a thumbnail drive and stick it in your computer and transfer files that way. If you have been doing that, right, then get into we're a quarter of the way into the 21st century. Join the rest of us, please. Right? You're engineers. You're not office drones, right? That's what office drones do, right? You have proper systems here. So you will need to be using it. Again, we'll only touch the surface. For example, some people had problems in their first hack or whatever because they would make changes, push changes. Their partner would push changes to their GitHub repo, and then they'd make changes, and now they've got a conflict between those two. Right? That's we never really cover merging or rebasing or these other advanced techniques. And so you really should get into it and learn those kinds of things. I think that there on the Canvas there are a couple of GitHub or Git tutorials. There are plenty of online websites that say, okay, well, I've got myself into this situation. What do? I've got a merge conflict. How do I go about resolving that conflict? Right? You've also seen build systems. This is more recent, right? Build systems are systems that allow you to build a complex project and maintain a complex project without having to type much, right? In C, we were using make or CMake, CMake. Right? That's the more modern version, right? With Java, or somebody used it. I forget who used it, but somebody in Java, somebody was playing around with it in Java. What was the equivalent in Java? Oh yeah, what was it? Okay. Hold that thought for a second. That's going to be a dependency management system. They were using Ant, right? Ant is a full build system that says, all right, we're going to build this file and put it over into this directory, and then we're going to build that file and put it into that directory. Then we're going to package it all up into some sort of jar file, which is a Java archive file. That's what you'll do next semester, actually. But we never actually used Ant directly because under the hood, Eclipse is doing that for you. Right? In fact, I think that there is a default system-wide Ant script for Eclipse that ends up doing it. So it's neither one of these things are something that you have to learn in this course, but these are tools because if you have a project with hundreds of files, right, and they all have to be built in a certain order, you don't want to sit there and be typing it out every single time on how to build this stuff. So you put that into a file, like a make file or an Ant build file, and then you just simply click a button and it does it for you. In fact, you can get really much more complicated if you want to with Ant or even Make. It can go out and grab new dependencies, build with those new dependencies, and even deploy to a system all with the click of a button, right? This gives you something called DevOps. In fact, this could be an entire job. In fact, it is an entire job in a lot of places. In fact, it's been a long time now, but back when I worked in industry, we had maybe 100 actual developers, but then 2 of them were dedicated to nothing more than, we didn't call it DevOps at the time, but that's what it's called now. They didn't write any code. They just wrote code to maintain everybody else's code. They were responsible for deployment scripts, the scripts that went out to like a pre-production system or a test system or something like that, so that nobody else had to worry about the entire process. They just had to write their code, hand it off to another team to write test code, JUnit stuff, and then hand it off to another team to make sure that everything worked correctly. Yeah. Oh, this is at Werner Enterprises. It's a trucking company up in Omaha. And even though it's a trucking company, they had like 300-person staff and stuff of developers, right? Why? As I've said before, there is no company that is not an IT company anymore, right? If you do not have a substantial staff of developers, of programmers or whatever, then you're a company that probably is not going to survive another 10, 15, 20 years or something, right? Unless, of course, you're just outsourcing everything, right? So again, entire teams can be dedicated to this. Here's another acronym. We love acronyms in computing. CI, continuous integration. Something more akin to that in Java would, of course, be Jenkins. It's an entire system that is built on, I think it's built on top of Ant, don't quote me on that, but it basically allows you to also deploy to systems, and you just make one change and you hit a button, it runs all your tests, and if the tests pass, then it automatically commits that change, and then if the change is committed, then it deploys it to a test system immediately so that you don't have to worry about these details. Right? Now, something that you just mentioned back there are dependency management tools, right? So, for example, apt, right? Or apt-get, right? You use this directly when you had to install CMaka on your CS50 IDE. Why? Because it was not a standard library that came packaged with that system. And so apt-get is a way that it says, I want to install this standard software. I don't want to have to download the code, build it, like make, right, or compile it, and then install it into my system. I just want somebody else to take care of that for me. And so you have these dependency management systems, these package management systems. This is a package manager, right? That can also look at dependencies and say, well, to install that software, it has a dependency on that software and that software, and that software has a dependency on that software. Super, super complicated. So what we do is we put that all into a package manager that goes out and gets all of those transitive dependencies and installs them all in the correct order in the correct way. In fact, again, I'm taking this course, this meta course on software performance engineering, and they asked, well, what could, they use this this tool called Silk, C-I-L-K, to be able to do parallel programming easy. And they were asking us for feedback, and I said, well, you know what? It would be much easier to use this thing if you actually had it in a standard package manager, because as it is right now, you have to download it from their website, you have to build it for your particular system, then you have to install it, and you have to troubleshoot and make sure that everything works. That is a huge, tall order to get into something where, as an alternative, there's another library that does the same thing called OpenMP. All I have to do is apt-get OpenMP, and I'm done, right? So which one of those things is going to win out in the end? The easier one, right? There's also, every language or every system has something like this. You mentioned in Java, what is it? Maven, right? In fact, you can go to Maven Central, and that's where all the software is stored, all these jar files and source files and stuff like that. But in a tool like Eclipse, what you can do is you can just say, Maven, get me all these dependencies. You kind of did that when you did your Hack 6 in Java, right? You had to click and add a library, and it was JUnit, right? It did all that stuff in the background for you. You weren't actually using a direct Maven dependency or a Maven tool, but Eclipse was in the background, right? Some of you have had Python experience. Python, right? What is that tool in Python? Yeah, pip or pip3. Yeah, for Python 3. I'll just call it pip, right? That's Python packet. Python packet. What is the I for? I have no idea. I don't remember what that stands for. But basically, these are all package managers, and it says, I want this thing to be installed so that I can have the libraries and stuff like that, and it does it automatically for you. Right? What do you know what it stands for?
Preferred installer program.
Okay, Python's not even in it. Preferred installer program. Cool. Right. Another tool that we've recently looked at is unit testing. Right. We started out with ad hoc testing, right, where we just ran the program on a particular input. That's when we were stuck with input-output programs, right? Then we graduated to informal unit testing, right? You write the boilerplate code, right? The code to set up the variables as input, the variables as expected output, run the test, compare them, and add a counter to the number passed or add a counter to the number failed. We realized that really quickly, I don't like writing boilerplate code because what I'm doing is copy pasting. So instead, we have formal unit testing frameworks like CMaka, or in Java, JUnit 5, of course. don't look back to JUnit 4 or older stuff. JUnit 5 is where it's at. Just like never program anything in Python 1 or Python 2, right? In fact, Python 2 reached, several years ago, it reached its end of life or end of support cycle, right? So definitely you should not be writing anything old school Python 1 or 2. And as far as JUnit goes, JUnit 5 is the current version. And you saw hopefully how easy that was to use with our examples. All you have to do is annotate something and say, this function is a test, right? And it takes care of all that boilerplate stuff for you. It's a little bit more complicated in CMake because it involves something called function pointers, which we haven't gotten to. But that's why we gave you that starter file so you can just follow those patterns, right? But again, these formal unit testing, that's where all testing is usually done. Now, of course, you can have something called TDD, right? And there would be a lot of TDD advocates or TDD, I don't know, enthusiasts maybe, all right, where it's test-driven development, that they would demand that you write all of the JUnit stuff before you even pick up a pencil, so to speak, to start writing your actual code. That's a little bit pedantic because, again, I look at it like the MC Escher drawing, where your tests will inform your implementation informs your tests, and it's a continual process of this back and forth. Right? Remember the MC Escher thing, right? The hand drawing the hand? All right, good. All right, so then we've gotten into static analysis tools. There we go, Static here means before you compile, compilation, right? It looks at your code for potential errors, right? Without changing it. It's a static, it's an unchanging artifact. And the examples that we've looked at so far are with GCC, the wall flag, right? Or they're sometimes called the extra flag, W extra. All means all to me, but all does not mean all to GCC folks, right? Because apparently here are all of the warnings, and oh, okay, there's some extras over here for some reason. But W extra is another thing that you can use. It's really more niche kind of warnings, but you can use it to as a linter, right? These give or make GCC a linter. Do you remember lint, right? That little specks on your clothes that are not dirty, it's just you don't want them there. It's probably something that you should take off, right? It can detect code smells, right? Remember, something can smell and still be good and still be okay, but it's probably it doesn't pass the sniff test. You probably want to take a closer look at it. Okay, after taking a closer look at it, yeah, that's exactly what I wanted to do. But that's why we call them code smells. All the time, there's food all the time that's great to eat, but stinks, right? My example would be Doritos. If you're not eating Doritos smell really bad. But if you start eating them, oh, okay, that's wonderful, right? So I don't know if anybody else has that same effect, but there are plenty of stinky foods out there that are still great. Here's another one in C. You can use a compiler called Clang or CLang instead, and it's got it's got a static analysis tool, analyze foo.c, right? And you can run this, and it'll when it's compiling, it'll go through all of your code and find potentially more stuff than GCC could. Now, they're always improving. So there's more stuff added to GCC all the time. There's more stuff added to Clang all the time. And so at this point, they're pretty much equivalent. But there are maybe a few things that Clang will identify that GCC won't, and vice versa. So that is yet another tool, right? Another one would be Facebook's Infer, right? It's a nice little tool that I was introduced several years ago, but it's not installed on your CS50, and it's probably too difficult to get installed. But back when we were using the CSE server, I had it installed so that we could actually use it. So if you're interested in stuff like this, what I would do is I would go to the GitHub page for this course, right? And if you go to documents, right? I've got this nice troubleshooting document. Where is it? We're troubleshooting. Here we go. It's a nice PDF on, is it going to render? Hopefully it renders. There we go. So, how to go about troubleshooting. Right? Basically what we've been doing. Their first line of defense against bad code is going to be to test. Write some tests. If it's ad hoc tests, fine. If it's formal unit testing, that's even better. Right? Then you use a linter, the wall flag. Right? Use a static analyzer like Clang, or like I just showed, using Analyze, or you can use the scanner, scan build, and basically it looks for things that when it translates it to machine code might be an issue, right? And then Facebook's infer that you can actually download and analyze stuff, right? So this is not an exhaustive list. This is just a list that I've built up over the years of things that are accessible. Facebook's infer is not that much accessible anymore unless you install it yourself. It used to be when we actually used it on our server. Yeah, restart that because we're going to need you here in a second. Right? But those are static analysis tools. What I want to focus on now for today and for Friday are going to be dynamic analysis tools. You've already seen one, but dynamic in this case means as it's running. All right. So we're going to analyze our program as it's running. After it's been compiled, it's sitting there, it's a bunch of machine code, we run it, and then we want to detect, well, does anything bad happen while we run it, right? And the example that you saw yesterday is Valgrind. Valgrind can be used to do a lot of stuff, right? To use Valgrind, compile with the G flag. Now, the reason that you want to compile with the G flag is because it needs to preserve line numbers in your original code. We've seen the compile process when you start out with C code and it compiles into assembly code and then it compiles into machine code. By the time it gets down to machine code, your variable names are gone. That variable that you called number of students, it's gone, right? It's just a register value now. That function that you called my awesome function, it's just a bunch of machine code now. And what about lines? Well, there are no lines anymore, right? It's just one string of binary, it was zeros and ones. So using the G flag will actually preserve all of that metadata about your original program, right? And then what you can do is you can run it, right? You can run Valgrind on your program by simply just going Valgrind, say a.out, right? If that's your program name, okay? If you've got some command line inputs, you can add those as well, and it'll take those command line inputs afterwards. But once you've run that, then you can do a lot of stuff. Let me demonstrate what you can do with it other than what you used it for yesterday, right? By the way, what did you use it for yesterday? Test for memory leaks, right? So let's go ahead and use it for other things. Let's see. So does anybody see the problem with this program immediately? If you do, stay silent. In fact, I'm going to tell the compiler, stay silent about this. The lowercase w actually shuts off all warnings, right? Demo.c. There we go. So all I'm doing is I'm prompting the user for an integer. I read it in, and then I echo it back to the user. A.out. 42. Segmentation fault. Now, does that process tell me where the error occurred, where the segmentation fault occurred? No. Now, you can probably guess where it occurred. Where? Line 17, because I forgot my ampersand. And if I had compiled with all of the warnings, including the extras, right, then it would have told me about that. You see the extras there, unused variables and stuff like that, right? But there's the actual problem there, that it expects a pointer. In other words, I want an ampersand in front of there. I'm not going to do the ampersand. Instead, I'm going to go to a world where the compiler didn't help me. I have a segmentation fault. Where the heck did it occur? Right? I'm now going to fire up Valgrind on this program, but before I do, I'm going to use the G flag. Right? Because if I don't use the G flag, let me show you what happens here. All right, and let's go ahead and run Valgrind on a.out. Right? 42. There we go. So It tells me that there's a segmentation fault, right? There were 2 errors from 2 different contexts here, but does any of that gobbledygook make any sense there? It's just a bunch of machine language, right? Just a bunch of hex codes and internal stuff. It does tell me that it happened in main, but where? What line? It has no idea because I did not compile with the G flag. So let's go back and compile with the G flag and preserve those line numbers. Now when I run valgrind, in fact, let me clear this out. There we go. And when I run with valgrind, I do get a full report on this. In fact, this is a stack trace. If you've ever had a problem in Java, right? Java, you end up with this red stack trace of it happened when this function called this function called this function. Now I'm getting the same thing. It happened when main invoked that scanf on line 17. I know that it happened in the demo.c file on line 17 here. That subsequently called scanf, and then it called this other thing, called this other thing, called this other thing. There's really no debugging down here inside of this stuff, right? Because it's all system level stuff. We'd have to actually open up the C libraries and start digging down deep. And I'm not going to go that far because I know that the problem is in my own code right here, right, on line 17. So if you have a segmentation fault, the very first thing you should do, fire up valgrind, find out what line number it's happening on. Okay. Now, you saw yesterday, I'm going to go ahead and get rid of this. Right? You saw yesterday that it can also be used as a memory leak detector. Right? Let me show you something a little bit more complicated than you did yesterday by using a 2-dimensional array. Int star star. Let's remind ourselves how this works, by the way. If you have a 2-dimensional array, you have a pointer to a pointer. And so here's my matrix or my table or whatever. And I'm going to call malloc, typecasting the return value there, on size of int star. Now, why is it not just a regular old integer? That's because it's not an array of integers, it's an array of pointers. You can go ahead and go int star or int space star, right? Once you've set that up, then you can start setting up each row. For int I equals 0, I is less than n, I plus plus. Mats of I is equal. Now here's your regular call to malloc. Malloc of size of, these are going to be integers. Now remind me, how many bytes does an integer take usually? 4. And how many have I done here? It's 3 by 5 matrix, so there are 15 in there. So how big is that? 60 bytes, right? Let's find out what valgrind says about this. I'm not even going to do anything about it. I'm just going to go ahead and compile it, right, with the G flag, and then I'm going to run valgrind on this. Right, there we go. All right, definitely lost and indirectly lost. So there's your 60 bytes, right, as you predicted, 15 entries, 4 bytes each, 60 bytes total. What are these 24 bytes though? Let's visualize. Yeah, go ahead.
Is it the actual array that holds the rest of the arrays?
The array of pointers, exactly. Let me come over here and visualize this in Python tutor with the C mode. Right, and edit this code. And we've seen this before. Let's go ahead and review it. Visualize this execution. On that first call to malloc, what we actually set up is an array of pointers. Right? 3 pointers to be exact. Each one of those pointers will end up pointing to a row of 5 integers. So I agree, all this stuff down here, that's our 60 bytes. What about this thing right here? 3 things, 24 bytes. How many bytes does each integer pointer take then? 8. Right? And that's pretty standard, right? Because it's a, have you ever heard of a 64-bit system? Right? 8 bytes times 8 bits in a byte, we have 64, right? Have you ever heard of 8-bit systems, right? Way back in the 80s, that's because memory addressing was only 8 bits instead of 64 bits. Right? You can do a lot with 64 bits, right? There's memory for days out of 64 bits. Right? All right, so let's go back to over here. All right, so it can be used to diagnose memory leaks, right? Well, you need to read the full report here, right? There were 84 bytes in 4 different blocks. 1, 2, 3 rows, but then also the array that pointed to each one of those rows. That's why it's 4 blocks, right? And where were they actually allocated? Well, on line 17 and line 15, right? So you jump over here and you say, okay, well, I allocated it on line 15. I also allocated something on line 17. Where did I actually free it up? I never did. That's why I'm getting a report for memory leaks here. Right? Now it's your job to go back in and decide, do I really care about this? Because I'm declaring it in the main, I don't. But if I'm declaring it somewhere else, I should clean it up. Right? Let's give this a clean bill of health now. So for, I'll use it right somewhere, and then I will free up the ith row. Right? And then finally, I will free up the entire matrix right there. Right? Now, when I compile this and I run it, I get a completely 100% free bill of health. Right? In fact, it tells me no leaks are even possible, right? Because you freed everything up. Right? Okay? All right. So let's see. One more use case here. Let me simplify all this. Right? And let's go ahead and go with a regular old array here. AR is equal to int star malloc, right? Of size of int, and I'm going to do 10 of them. So let me go ahead and create that variable and say 10. And then I'm going to set it equal to 10, 20, 30, 40, et cetera, for int I equals 0, I is less than equal to n, I plus plus. Uh-oh. Right? Already you know that this is wrong, right? Because that's not the usual idiomatic for loop. Fine. Right? This is going to be I plus 1 times 10. Right? Let's GCC this. And let's run it without valgrind. Perfect. Nothing happened, right? No segmentation fault. Worked on my machine. But we all know on that line, less than or equal to, there is something wrong there. Right? Valgrind can tell us that there's something wrong there. Right? All right. So there are definitely 2 errors in 2 different contexts here. Right? And of course, one of those errors is that there's a memory leak of 40 bytes, 10 times 4 integers. But what else do I have here? An invalid write of size 4. Size 4, what does that tell me? It's an integer. If it were size 8, it would probably tell me, oh, I'm doing something wrong with a double there. If it's size 1, that's probably something with a character of something, right? And it tells me that there is a problem where? On line 13. Or it was declared on line 13. Here's the actual problem, sorry. On line 15. Now that tells me that there's something wrong with that loop. You immediately look at it and say, oh, okay, well, I shouldn't have had that there. Right? But if it works on my machine and it doesn't work on somebody else's machine or on the grader or on code post or whatever, right, then probably there is a problem. It's just hidden. Valgrind can find it for you, right? Because we do try to set up the code post and the grader and stuff like that in order to, do very large arrays and stuff like this on a small array that's only 40 bytes. It's probably actually giving you an entire kilobyte, and it's only using the first 40 bytes. So you're only violating your own memory, and that's why it's not showing up as a seg fault. But when you do this on very large memory for megabytes or gigabytes or something, then of course it will result in a segmentation fault. So those are 3 kind of common things that you should be checking for. So common issues would be memory leaks, right? Invalid read or writes. By the way, it was a write because I was trying to write 110 to it. If I wasn't writing to it, but I was reading from it and I went beyond the bounds, then it would be an invalid read error in Valgrind. And the other thing was seg fault isolation. Right? Finding out what line number it happened on. What line did it happen on? Right? Okay. All right. And one last tool before we get to the other tool that I do want to cover is just a brief mention here of perf testing, right? You sound really cool when you say perf testing instead of the actual thing that it stands for, performance testing, right? You have things called profilers that will actually run your program and it'll say 90% of your computation time is occurring in this one function over here. If you want to look for an optimization, that's where you look to, right? And so you go into that function and you find out, oh, well, I was doing something really inefficient. I can go ahead and move this thing around and move this thing around, and now my performance is through the roof, right? It was taking me hours before, and now it's only taking milliseconds now, right? gprof, maybe we'll get to this later, but it'll be able to report stuff like 90% of your time was spent in this function, 5% of your time was spent in this function, 2% of your time was spent in this function. By the way, that there's this issue, you can even have what are called heat maps, right, where this section of code is really, really hot because most of your time is spent on that one line or something. And so you can actually use profilers along with visualization tools to immediately spot an issue and, okay, I'm going to focus all my attention right there. Right? Because, yeah, you can focus it on that 5%, but are you going to get a lot of return on investment on your time? Fine, you took 5% down to 1%, right? Where you could have focused on this 90% and taking that down to 10%, and now you're 10 times faster instead of 1.001 times faster. Right? And that all gets into performance testing or perf testing. Right? Instead, what I want to focus on today and Friday is on proper debugging. Right? And I say proper debugging because, of course, maybe the debugging that you've been doing up to this point, or maybe the debugging that you did in high school, was called poor man's debugging, right? Where you just put a bunch of printfs everywhere, right? And say, okay, well, what's going on now? What's going on now? You don't want to do that because it's extremely brittle, right? You constantly have to write and erase a bunch of lines. Okay, I fixed that bug. Now let's move on. I'm going to erase everything. Okay, now another bug came up. I need to restore all that print stuff that I had before. It gets really, really annoying really, really quickly. Also, it doesn't even really work. Right? With undefined behavior, anything can happen. So what you could do is you could have like 10 lines of code where you're printing stuff out on every other line. The error actually occurred on line, let's say, 8, right down here on line 8. But it appears to occur on line 2 because line 3 was never printed. It actually was. Right? The way that printing works is it doesn't immediately print to the screen. What it does is it takes this output and puts it into a buffer. You've all heard of buffers before. Buffering, right, when something's downloading or watching a video and it starts buffering, that means it's downloading more data in order to store so that you can actually watch it smoothly. Well, an output buffer is exactly the same. It's extremely expensive to print something to the screen. So it doesn't do it character by character by character. Instead, it dumps it to a buffer. And then it only does it when it feels like it needs to. It's called flushing. It flushes the buffer out to the screen, right? Because it's such an expensive operation. So you could have an error down here, and the last 5 lines of your print statements are still in the buffer, and you never know that it happened because it's stuck in the buffer and the buffer never got flushed. Right? So it is extremely brittle. It doesn't even work because undefined behavior is undefined behavior. Sometimes we call these things non-deterministic. We don't know what's going to happen. Anything can happen. Right? So it's not a proper tool to use. Instead, the proper tool to use is going to be, for C, it's going to be GDB. Right? GDB is short for GNU's debugger, right? GNU, does anybody know what that stands for? It's a clever, I don't know. It's an infinitely recursive acronym. GNU is not Unix, right? So what does that GNU stand for? GNU is not Linux. What does that G stand for? Well, GNU is not Linux, right? It's an infinite recursive acronym. Right? Computer scientists like doing stupid, clever stuff like that all the time, right? So it's GNU's debugger. It's a command line user tool. So you're all familiar with GUIs, or graphical user interfaces, GUIs. Well, this is different. It's going to be a text-based user interface. If you think, oh, that's way too old school, trust me, the biggest computing gurus in the world never see graphical user interfaces on their daily basis. They do everything at the command line. Because once you've learned to use the command line and use it well, you'll find every single user interface, regardless of how well designed it is, to be super clunky. I can do that in a couple of keystrokes. And once you get good like that, you never look back at another graphical user interface, right? So most sysadmins will not have graphical tools. They'll do everything at the command line. Our sysadmins do everything at the command line because it is so much faster. In fact, there are studies on this, that somebody doing something at the command line in Unix can do is 10 times more productive than somebody using a graphical user interface of some sort, right? So in particular, what is a debugger? A debugger is a program that simulates or runs your program, or another program, and allows you to pause. Because of course, programs are ephemeral. They are very, very quickly done and out and gone. All right, I've got somebody here. All right. There you go. So, do you want to tell us about it, or? Yeah. So we've got I'm the faculty advisor for the Game Dev Club. They're buying and delivering T-shirts right now, and so I was just paid for my T-shirt. But has anybody joined or is interested in joining? All right. Well, then tell us more about it.
It's not surprising you haven't heard about it. Even though it's kind of a small city after all. Basically, it's just we spend the semester working on our games, and like we pick out stuff. Basically, we have a pitch meeting where we show off the game ideas that we want to work on, and then we get people together in groups in order to work on those ideas for the semester. And at the end of the semester, we show what we got.
And it's judged. I get my kids to judge some of the games. And some pretty cool projects have come out of it. Some folks just continue to develop it. I think that one person from the Game Dev Club had something on the App Store. Several people probably have put their games on the App Store at this point, right? But you primarily use Unity or Godot or what?
Right now we're using Godot more.
Okay.
Some of the members are more familiar with Unity based on what they do, but you can use whatever you feel comfortable with.
Okay. So yeah, they gather on a Discord. I can provide an invite link to everybody later on. But thanks for coming by, and I look forward to seeing my T-shirt.
Yeah, I'll get that to you.
All right, it's been about 4 years since we've had T-shirts done, but I still have mine from 4 years ago. So you might still be able to get a T-shirt. Maybe you have to wait for the next round. But clubs and it doesn't necessarily have to be games. If you're not into games, that's fine. But I would encourage you to get involved in some way. Right? There's also OS2G. They're big into open source software. They have Linux installation clubs or events or whatever. What else is there? There's Corn Hacks, which is going to be in January, I think. January, or maybe it's February, I forget. But it's a 24-hour, 48-hour, I don't remember, 48? All right, 24-hour hackathon. So you form your groups. The second place prize last year was Legos, and they realized that nobody wants the keyboards, they want the Legos, and so we're going to make that the first place prize this year or something. And they get a lot of corporate sponsors. Even if you don't want to go for the grand prizes, it's a nice little event that you can attend, get free food, have some fun and stuff like that. Other people in here are even forming new groups to do stuff. And so if anybody has a group that they've joined or they want to promote, just let me know and we can talk about it. Right? But anyway, sorry for that digression. But anyway, back to debuggers. Right? Debugger is a program that simulates or runs another program. Again, allows you to pause execution because programs are ephemeral, that is quick-lived. They die very quickly. And so you want to pause it and take a look around and see what kind of variables that you've got, right? What are the variable values that I've got at this point in the program? It allows you to even evaluate expressions, right? Okay, the variable value x and y, well, what happens when I multiply x and y together? Or I divide, okay, I'm going to get a division by 0 there, right? It allows you to step through a program line by line at a human pace in order to start diagnosing issues. Right? So again, the usage here is you're going to have to compile with the G flag, because if GDB doesn't know what line number it's executing, you're not going to be able to know what line number is executing. To run with GDB, you use it just like Valgrind, GDB a.out. Right? Let me go ahead and walk you through we're not going to be able to walk through a full program here, but I'm going to give you a preview. So I already compiled that program with a G flag. Let me go ahead and fire up GDB on a.out. All right, I'm running GDB right now. Right? It's not very impressive when it starts. That's all right, we can make it more impressive. I'm going to take some real estate up here. Right? What I can do is I can start looking at my actual code, layout, SRC. Right? So there's my actual code. I'm hitting the up, down, and the down button, right? This is my code that was compiled, but everything was preserved so we can actually see it. Right? Now, if I just run this, of course, it's going to run through the entire thing, right? And exiting normally. I don't want to do it. I don't want it to do that. I want it to pause at a certain point. And so what I'll say is pause at line 12. What that does is it sets a breakpoint. Did you see that little B plus right there? That breakpoint. Now what I can do is I can run, and instead of running all the way to the end of the program, it stops at line 10. It pauses. And I can take a look around. Print n. Oh, n doesn't have a value yet because line 12 is not executed yet. So let's execute that. Next. There we go. Now print n. And we see that it has a value of 10. Right? In fact, next is such a common step that you just echo n. Right? You can type out next if you want to, otherwise just n. Right? N, 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 n. You see it executing this for loop over and over and over again, right? Because I is still 4, and so it's less than or equal to 10, and so it's going to continue to execute, right? So you can do a whole bunch of tricks like, for example, I could watch I, right? So as I go through this loop now, anytime I is updated, it tells me about it. It was 4 before, but now it's 5. Next, next. Oh, now it was 5 before, now it's 6, right? Et cetera, et cetera. So we will look at this in more detail. I'm going to bring a really buggy program, and we're going to diagnose all the issues together as we walk through a debugger like this. The last thing I'll tell you is, well, okay, how do we get out of this, right? You can go ahead and just type quit. Oh, quit. Qui is good enough, apparently. It's got command executions or completion, so if you just type Q, it'll probably quit. And do you really want to quit? Yes, I do want to quit. And it takes me back to the regular command line here. Right? The equivalent to that over here in Eclipse is going to be, as we've seen before, this little bug up here. Right? But that's a graphical user interface instead of a text user interface. Right? Every language is going to have a debugger attached to it somehow. Python folks, have you used a debugger before? What was its debugger? Does anybody remember? No? Don't remember? Okay. It was probably integrated into the IDE that you were using anyway. So it probably doesn't have a name. It's like, what is it, PyBooks or what? Yeah. PyBook? Okay. And so everything it's just PyBook, right? There's no special thing in it, right? All right, we'll continue there on Friday.